In this question, a scientist has a potassium hydroxide solution of known concentration and a hydroiodic acid solution of unknown concentration. The scientist uses the potassium hydroxide as the titrant in the burette and a known volume of the hydroiodic acid as the analyte in the conical flask. So just to get a better idea of what's happening here, we're starting off with hydroiodic acid in the conical flask, and we're adding potassium hydroxide to that. Remember, in titrations, we use an indicator to determine when the pH changes through an important point. Since this is a strong acid, strong base titration, that's going to happen at a pH of 7. So we've got the molecular version of the chemical equation shown here. I'm also going to write out the complete ionic equation so we can get a better idea about what's going on. So HI, hydroiodic acid, is a strong acid, meaning it's going to split up into its ions completely when it's in solution. Then we have potassium hydroxide, which is a strong base. So again, it's going to split up completely into its ions when in solution. Then we have potassium iodide, which is a soluble salt. So again, it's going to completely split up into its ions in solution. And finally, we have H2O, which is a molecule. So that stays just as H2O. So looking at this, we can see that K plus, the potassium ion, and I minus, the iodide ion, both appear on the left and right of the equation. That's telling us those are spectator ions. So they're not actually participating in the reaction. Whereas the H plus and OH minus ions, those are participating in the reaction because they're reacting together to form H2O water. Now on our graph here, we have the pH, and that's the pH of the solution in the conical flask. So because we're starting out with just acid in there, we're expecting to have a low pH to start with, which is what we see here. It's starting out way down here. And then as we're adding the potassium hydroxide, the pH is going to increase until we reach the equivalence point. That's the moment where the acid in the conical flask has completely reacted with the added potassium hydroxide. And therefore the pH is going to be 7 since we have a strong acid and a strong base. So that's going to be this point here. Then we keep adding potassium hydroxide and our pH is going to keep increasing up to the numbers higher than 7, showing that we have a basic solution. So now we need to go through the graph and figure out which species are present in significant concentrations at each point during the titration. So I'm going to draw a representation of what's going on in our solution at each moment. Let's start by looking at point A. So at this point on the graph, we have 0 liters of potassium hydroxide added. So we just have hydroiodic acid in our solution. So I'm going to show that in my box here. Remember, hydroiodic acid is a strong acid, meaning it completely splits up into its ions. So I'm going to have some H plus and some I minus. I'll just draw a few of these. So there I've got 5 H pluses and 5 I minuses. I'm not going to draw the H2O in here just to make it a little bit simpler to look at. So that's all we have in here at the beginning. We have hydroiodic acid. Because it's strong, it splits into its ions. So looking at our box here, we're going to have H plus and I minus in our solution. Next, we're looking at point B here. So at this moment, we've added 0.03 liters of potassium hydroxide. So let's go ahead and draw in, let's say we're adding 3 potassium hydroxide. Again, potassium hydroxide is a strong base, so that's going to split up into its ions. So you might think here that we'll have K plus, I minus, H plus and OH minus. However, looking at our chemical equation and our complete ionic equation that we wrote up here, we can see H plus and OH minus are going to react together to form H2O. So any H plus and OH minus that are there are going to react together. So these pairs are all going to react together to form H2O. But we already decided we're not going to include H2O in our diagram here just to make it more clear, so I'm going to get rid of those again. Okay, so at this point we have H plus and I minus still. We've got less H plus than we did, but H plus is still there. And we have also some K plus. So now we have H plus, I minus, and K plus. That makes sense because we still got some concentration of H plus there, and our pH is less than 7, meaning we're acidic. So that makes sense. Next, let's look at point C. This is a point where we have 0.05 liters added of potassium hydroxide. And this is the moment where we have a pH of 7. So that is the moment where all of our acid has reacted with base perfectly, so that all the H plus has been used up, reacting with OH minus. So I'm going to need to add, since I've got two H pluses here, I'm going to need to add 2 more sets of KOH. Again, potassium hydroxide is a strong base, so it splits up into its ions. And then again, any OH minus H plus pairs are going to react together to form H2O. But again, we're not going to show H2O on our diagram just to make it a bit simpler. So now at this point, we've got K plus and I minus, and that's all we have in our solution in significant concentrations, I minus and K plus. The reason why is that all the H plus that was there has completely reacted with the OH minus that's added. Okay, next at point D. So this is where we've passed that point where we have the reaction completed and we're adding more KOH. So let's go ahead and add that in here. I'll add 3 sets of K plus and OH minus. So the K plus we know is going to stay as its ion because that's a spectator ion in our reaction. The OH minus would react with any H plus that's there, but we don't have any H plus. We're just adding more OH minus. So the 3 things that we're going to have present at D are going to be K plus, I minus, and OH minus. Finally, at E, we're just adding more potassium hydroxide now. Now we've got 0.1 liters of potassium hydroxide added. So I'm just going to add some more potassium hydroxide, more K and more OH minus. So the composition of our solution hasn't changed. We've just got more K plus and more OH minus in there now. So it's going to be the same as the last one. We've got I minus, K plus, and OH minus. Awesome. Okay, so we've gone through and figured out what species are present in significant concentrations at each point. Next, we're asked, when does the equivalence point occur? So the equivalence point, that is when the analyte, that's the substance that's in the conical flask, has reacted completely with the added titrant. And remember, the titrant, that's the thing that's in the burette that we're adding to our conical flask. So the way we tell when the equivalence point has occurred is by using our pH change. Here, because we had a strong acid and a strong base, the pH is 7 at the equivalence point. So when does the equivalence point occur? Well, we know it's going to occur when the amount of analyte is the same as the amount of titrant that was added. And in this question, since we have a 1-to-1 ratio of acid to base in our reaction, we need the number of moles of KOH added to be equal to the initial moles of HI. That point is point C on this diagram. We know that because the pH is 7, and since we have a strong acid and a strong base, the pH is going to be 7 at that equivalence point. The reason why is that at that moment, all the H+ that was in our analyte, the hydroiodic acid in the conical flask, has reacted completely with the OH- added from the potassium hydroxide, which is the titrant, so that it's been neutralized. And we're just left with K+ and I-, which are not acidic or basic ions. So in this skill, you need to go through each moment shown on your graph and figure out what you're going to have present in the solution at that time. Remember that strong acids and strong bases dissociate completely in water, meaning that they're always going to show up on your diagram as H+ and I-, or K+ and OH-. They're never going to show up on this diagram as HI or KOH because they're going to immediately dissociate when they're in water. Also remember, for strong acids and bases, the equivalence point will always happen at a pH of 7. That's the moment where the acid and base have reacted completely with each other so that the solution is neutral.